Hello, everyone. Welcome so much for joining us today. We're thrilled to have you here for a jam-packed agenda talking about mechanical storage, long duration energy, and the very different types of way to promote pumped hydro. I'm also looking at some colleagues making sure, can you hear me?
Yes.
Okay, great, thanks. Okay. So I'm Julia Sutter. I'm the CEO of the Long Duration Energy Storage Council. Thrilled that you're all here and just want to jump in to really highlighting the important role that we're all playing in addressing climate change and really trying to move as quickly as possible, scale up long duration energy storage. As we're all feeling around the world, we've been having constant weather patterns and weather climate events, whether it's increased droughts or increased heat patterns, or whether it's increasing very, you know, um, wildfires. I mean, just around the world, every community has been affected by the changing in the climate. And so as we're really trying to move towards more renewable dependent climate energy, if you go to the last slide, please, the really trying to promote that we need this greater flexibility. And so we're working all together as the council to really achieve our global net zero targets. And we're doing this to really expand the marketplace, provide societal benefits, and really look at this diversity of long duration energy storage. What's also really great about long duration energy storage is that it really does touch every community, every part of our infrastructure in our industry, whether you're looking at agriculture, transportation, whether it's buildings, commercial. And there's so many different elements that really kind of connect us all to the need of this transition. And again, how valuable long duration energy storage is to addressing this security, the resiliency, the reliability, the affordability, and again, that flexibility that we're going to depend on and that we do today. And just really wanted to highlight there's so many great speakers today from our member companies really promoting their diversity, but it's also really exciting just to see how much development is happening and continues to happen on long duration energy storage in the Americas and Asia Pacific and Europe and the Middle East and Africa. And when we're talking about long duration energy storage, we're really focusing on power, heat, and hydrogen. And today we're really going to look at the different types of power and that the benefits that really come from long duration energy storage are reducing curtailment, really trying to give an integrated system, providing different pathways to look at the energy system through transmission distribution. And again, have that whole kind of energy system flexibility that is so critical as we incorporate more renewable energy. The great thing about long duration storage is that we really can provide that 24/7, every hour of every day being met with clean energy. And the council provides this unique perspective because we bring together diverse technology providers that represent chemical, thermal, electrochemical, and mechanical. And then we also have our customers, industry services, capital providers, equipment manufacturers, integrators, and developers all working on this ecosystem to really promote the diversity of long duration and the market and the capabilities that are available that we need to start, really accelerating today. There are many types of long duration storage that have been commercial, especially pumped hydro for over a century, and that we're really building on this expertise and knowledge to really bring worldwide benefits of LDESS. So we have 4 reports that are posted on our website, that go into the $4 trillion market of long duration energy storage. We have, the kind of net zero power and net zero heat analysis. We have a public policy toolkit with over 20 policy recommendations and the 24/7 Clean Power Purchase Agreement report. There's a ton of great information in there. You can always reach out to us if you have any questions. But we also, in addition, talk about the scaling up and the tools, but also the $540 billion of savings that you can get annually with LDESS. And so today we're going to dive deeper into mechanical long duration energy storage. And these are our member companies that really, again, promote this diversity of different types of mechanical storage that we're going to really hear from each of them and their unique characteristics and their value add to their communities and then around the world. So as you all know, pumped hydro storage is the most widespread, it accounts for over 95% of the total energy storage capacity worldwide, which is really great. Today, you're going to kind of see also advancements and new innovations that are emerging from this grown expertise. And there's also compressed air energy storage that can be underground or above. And it also can include thermal storage to store the heat. So again, that flexibility and really kind of bringing the different components to really advance the energy systems. And then we also have gravity-based energy storage, lifting mass up and down. liquid, and whether it's liquid CO2 or other types that really kind of focus at storing at high pressure and then changing the temperatures and then releasing a turbine. Also kind of having closed looped, and all of these really have low emissions or zero emissions. And then liquid air storage, using cooling and tanks and kind of changing again the pressure. So you're going to hear from each of our members kind of dive into this more. But again, it's really important to note the diversity that's available, so that we can really meet locally what we need to address, the flexibility, the system reliability, security that long duration energy storage can provide. So I'm going to hand it over to our members and let them dive a little bit deeper. And please add your Q&A into the Q&A tablet, and we can address them as we go through, and we'll have some time at the end for additional Q&A. So thank you all again for joining us, and look forward to a great conversation. And I hand it over to Chris at Breeze.
Hello, everyone. My name is Chris Connors. I'm the Chief Operating Officer of Breeze. Breeze is a distributed long-duration energy storage system. It's called CAPS, and it is a CAES technology. I'm sorry, go ahead. It's a compressed air pipeline system. We use CAES technology within pipelines to store, transport, and generate electricity. In this diagram to the left, over here, you'll see that we're using renewable energy solutions in order to generate electricity. We take that electricity and we run compressors to compress the air and place it in the pipeline. During the compression stage, we generate a lot of heat. And so some of that heat is reused in our compression stage to make it more efficient. And some of it is stored in this little orange thing in the center. It's a heat sink to be used later on. When the energy is needed again, later on, we release the air. It comes out about up to 700 pounds per square inch. And it's thrusting out very cold. So we have to warm it up through the heat sink before it is thrust on the turbines to turn a turbine and generate electricity. We warm it up for two reasons. One is it expands the air and increases volume that helps improve our efficiency. And the second reason is it warms up the air so it doesn't freeze the turbines. That's a very good reason. Next slide, please. There are 3 million miles of oil and gas pipelines in the United States, of which about 25% are idle. In the picture to the right, you'll see one of the pipelines that we have that we're going to be using. This is a main pipeline, which means it's 16 inches or larger in diameter. This particular pipeline is 34 inches in diameter and 1,100 miles long, and it is all currently idle. If we took all the main pipelines that are idle, that's 125,000 miles of idle main pipelines, and we ran Breeze technology and all of that, it would be able to store 500 gigawatt hours of energy at any given time. Next slide, please. There are a lot of benefits of using Breeze. Obviously, as just told you, it could store lots of energy, weeks of inertia energy, and we could store it for months on end. Because we're using idle oil and gas pipelines, they are designed to take fossil fuels and move them from one point to another along the pipeline. The other one is 1,100 miles long, which means, of course, we can have intake and offtake locations that are hundreds of miles apart. It also means that all along that pipeline, we are able to have multiple intake and offtake locations, which can support different types of services and different solutions all along the pipeline. Think of it as an energy highway. And as you can see right here, that represents other storage facilities of CAES technologies. We can also be used for other CAES storage technologies to put their compressed air into our pipeline, use us for transport. And of course, if we have multiple intake and offtake locations all along the pipeline, that means we can simultaneously charge and discharge at the same time. One of the biggest advantages of the Breeze solution is that we're using existing infrastructure. The pipelines are already in the ground. They're already connected to the grid. There's grid connections all the way through it. We're using off-the-shelf equipment, which means that we can build now and we can deploy the solution rather quickly. Next slide, please. So some quick performance metrics. Breeze will be compressing up to 700 PSI. The gas pipelines that we're using and oil pipelines are rated for 1440 PSI, so we're well below that rated system. That'll extend the life of the pipeline for our usage. Our round trip efficiency right now is between 60 and 70%. although we believe shortly we'll be above 70%. We're able to store vast amounts of energy with minimum degradation. And then within our solution, if the heat from the compressor is close to an expander, this can be 100% clean energy solution. Next slide, please. So here we are. Here's where we are now. We just completed our small prototype. It cost us $150,000. It's a 5 kilowatt hour scale 1 to 20. It's the picture of it. The design is on the left, and the actual testing pad of where it is right now is the center picture. We have a larger prototype, which is in the upper right-hand picture. As representing, that's due in the end of August. So it'll be a TLR6. That's costing us roughly $300,000. It's using a 3-kilometer pipeline that's 8 inches in diameter. And we have a commercial pipeline for our first commercial project that is expected for February 2024. It is a 5 megawatt system. It'll cost $10 million. It is for using a 26-inch pipeline that is 16 inches in diameter. Next slide, please. I thank all of you for your time. I look forward to your questions.
Hi, everybody. My name is Francesco Oppici, and I'm co-founder and the Chief Product Officer of Energy Dome. I'm here to talk to you about our innovative technology for long-duration energy storage. If you can go to the next slide. We like to start our presentations from here because this is a very important milestone of our business development. In fact, this represents the first commercial scale plant operational. It's a 2.5 megawatt, 4 megawatt hour plant that we built in Sardinia. It has been connected to the Italian national grid and operational since May of 2022. This for us represents the last step of the risking of our technology before commercialization. In fact, the 2.5 megawatt is the minimum size for us to have the right type of compressor and turbine, exactly the same type that we are planning on using on the full scale commercial plants that we are now in the phase of commercialization. In the next slide, you will see how this system works. So this is a closed loop that uses CO2, carbon dioxide, as a working fluid. In its ready for charge state, all of the CO2 is confined at atmospheric temperature and pressure into a dome, which is exactly the same type of domes that are used in biogas application. When we want to charge the system, we start drawing power from the grid or from any source of energy, of electricity, and we start compressing the CO2 that now flows from the dome into liquid CO2 vessels. In fact, after compression, we store the heat of compression, and then we condense the CO2 at ambient temperature at high pressure. In charge phase, all of the CO2 is moved from its gaseous state in the dome into the liquid phase into the high pressure liquid CO2 vessels. And in this charge phase, we basically invert the process. So we take the liquid CO2, we re-evaporate it, recover the heat stored in the thermal energy storage, and then expand the hot and high pressure CO2 into a turbine, and then produces power back to the grid with a 75% round trip efficiency. The reason for us to use CO2 is because it's a fluid. Maybe you should mute yourself. I have an echo. Yeah, so sorry for that. The reason for us to use CO2 is because it's a fluid with a critical temperature of 31 degrees C, which means that if pressurized, it can be liquefied at ambient temperature, meaning that we can reach very high round trip efficiency and very low cost of deployment of our technology. If you go to the next slide, please. Currently, Energy Dome is commercializing our standard module, which is a 20 megawatt, 10-hour duration, actually 25 megawatt on the compressor and 20 megawatt on the turbine. This kind of compressor and turbine are exactly the same type of compressor and turbine that we have used into our commercial demonstration project. And all of the equipment that we deploy in our technology are actually available from tier 1 reference suppliers, which are not only ready to supply this equipment, but also guarantee its performance. We are going to have a very similar approach to wind turbines, in a sense that we will deploy. We have developed a standard frame of 20 megawatt at 10 hour, and we can scale this frame in multiple units in order to scale the total capacity installed into our systems. And in the next slide, I'm going to summarize to you the main, let's say, advantages of our technology, which include a 75% round-trip efficiency, AC to AC, medium voltage to medium voltage. This is a proven technology which has been operational already from 1 year, connected to a national grid here in Europe. It is cost effectively. Actually, it is today about half the capex of lithium-ion batteries. It is durable because we just use a thermodynamic process. Our system can last without degradation over 30 years lifetime. And it's reliable because it just uses off-the-shelf components which are quickly deployable and scalable at the same time. And also site independent because it can be deployed without any specific site limitation or site requirement. Thank you very much for listening to me, and I will be happy to reply any of your questions.
Hello, this is Dean Toole with Hydrostor. I'll take you through our technology over the next couple minutes. If you just go to the next slide. The company was founded about 12 years ago. We take traditional case and form it into what we would call advanced case, where we've enhanced a few of the primary characteristics of it and removed, made it an emissions-free technology. Company's backed primarily by Goldman Sachs and the Canadian pension fund. We raised about 1.5 years ago, about 250 million from Goldman. If you go on to the next slide. So, traditional case has been around for about 50 years plus. There's two main projects that people usually refer to, one in Germany, one in Alabama. Those together are, over 300 megawatts, quite large in scale, but they're dependent upon two main characteristics that we have removed from our process. One, they use existing salt caverns to store the compressed air, and then they also remix natural gas usually into the process when they're discharging or heating the compressed air to turn the turbine. Next slide, please. In our technology, what we've done is we've patented a few processes, and I'll take you through kind of a 5-step process that makes us a little bit different. But first of all, on the left side of this slide, you'll see a sample project that we have, the 2 megawatt project outside of Toronto. This project actually has a contract with the ISO, so it is commercially viable. It is also a long duration system, but it did prove out some of the key characteristics that I'll go through here in just a second. So first, to kind of take you through the general process, like traditional case, we compress air usually using off-peak hours. Primarily, we would expect those to be renewable electricity generated hours. We take that compressed air and the heat that is generated from the compressed air. We take that heat and we store the heat. So there's a lot of heat generated from the compression stage. We then pump the compressed air down into a cavern. The caverns that we use that would be different than traditional salt caverns. We can drill out those caverns in pretty much 60% of North America, anywhere where there's hard rock. And these are caverns that have been used in the hydrocarbon business for tens of 20, 30 years. There's roughly about 200 of these types of caverns around the globe today. So as we pump the air down into the cavern, it displaces water. So it's a closed loop system. The water is then pushed back up to a reservoir up above. And then we would consider, once that compressed air is fully contained within the cavern, we consider the system fully charged. We then, once we want to generate electricity, we would release the compressed air, remix it with the heat that we captured earlier in the process, and that would be used to turn a turbine just like a traditional gas-fired plant, or also something akin to pumped hydro when you're running water back down through the system. We also would provide similar type services, I would say, to that of a traditional gas-fired plant. Next slide, please. So some of the key things that we look at in terms of how we provide, we really look at ourselves as truly a long duration 8-hour plus system. Really our sweet spot is certainly 200 megawatts and above. We're looking to capture some of those excess hours, usually referred to as, say, a duck curve, where there's excess renewable hours being generated. We'll take those, capture them, and then redistribute those to balance out against load and provide certain ancillary services to the grid. I think that's all that I have. Just a couple of highlights I mentioned before we leave. This project here in California is in mature development. We've actually secured a PPA with one of the CCAs out in California, currently in negotiations with some of the other major utility companies that people are familiar with. We expect this project to close in 2028. It's a 500 megawatt, 8-hour duration system. Some of the advantages that we have are similar to what some of the other friends of mine on this call have mentioned. One, we're emission free. We're also a 50-year plus asset. So on a per kWh basis, we're very, very competitive, actually cheaper than batteries would be. We would continue on an ongoing basis to employ probably 25 to 50 people at the site, roughly about 700 people we'd expect during the construction phase of a project. And I think that's all we have, and I appreciate your time.
Hello, everybody. My name is Ashok Krishnan, and I'm from Sumitomo SHI-FW. So the title of the presentation today is Carbon-Free Flexibility, and I will be sharing some details of our liquid air energy storage technology. Can we move to the next slide, please? So a quick word about who we are and where we come from. So we are a part of Sumitomo Heavy Industries, which is headquartered in Tokyo, Japan, and SFW itself is based in Espoo, just outside of Helsinki in Finland. So we are a pretty global organization with about 1,800 people and have a history of executing about 800 plus projects worldwide. Across the Americas, Europe, as well as Asia. We have our own manufacturing facilities and a global supply chain with a lot of partners and vendors with whom we work with closely. Can we move to the next slide, please? So coming to the technology itself, so we basically do liquid air energy storage. So as the name suggests, we try to store energy in the form of liquid air, and similar to the technologies which have already been presented earlier today, we try to use excess renewable energy, which is available typically if you look at it maybe from solar during the daytime, and we basically use ambient air which is all around us, and use the electricity to run a compressor. So the compressor basically compresses the air to a high pressure, and the heat which is emitted during the compression process is stored in multiple heat storages. So there is a high temperature heat storage upwards of 400 degrees, and a slightly a lower temperature heat storage. So even after the low temperature heat storage, there is still excess heat available, which could potentially be plugged into a district heating network to further increase the utilization of the heat there. So once the air is compressed, it goes through a liquefaction process, and the liquefied air is stored in highly insulated tanks where it can stay without any significant degradation for a couple of weeks even. So when we need to discharge, we utilize the liquid air, we pump it and use the heat which was stored during the compression process to evaporate and superheat the air, and expand it through a multi-stage turbine, which is connected to a generator, and then we generate electricity, which is exported to the grid. And in this entire process, the only so-called fuel which is used is basically clean air, and there is no emission associated with any of the processes. So as you can see from the schematic and from the description, it's fairly well-established processes and equipment which have been used in industry for a few decades already. And the whole plant can be set up in a very small area. It's quite compact, and there are no geographic requirements to set up the plant. And the lifetime is rather long. It's about 30 years plus, and there is going to be negligible degradation in the capacity. And the fact that we have rotating machines on both the liquefaction as well as the power recovery stage means that we have potential to provide a number of ancillary services to the grid, which is in addition to the routine energy shifting, which can basically be done by all the storages. And the recovery of the compression heat, as well as the cold during the evaporation process, which is stored in a cold storage tank, allows us to attain higher efficiencies. And the cold, which is stored in the cold storage tanks, is further used during the liquefaction process. So we like to say that the liquid air energy storage is scalable, ultra flexible, and location agnostic. So the next slide, please. Sorry, can we go to the next slide, please? So as I mentioned, we have a pretty compact setup. A 50 megawatt discharge, 100 megawatt charge capacity plant would require no more than 5 acres, which is a fraction of the land you would require for a large renewable energy plant. And if we move to the next slide, so our first commercial demonstration plant is coming up in Hiroshima, Japan, in partnership with Hiroshima Gas Company. This will be a small plant, 5 megawatt on the discharge side and 4 hours of storage duration. And this will be co-located with an LNG terminal, and will reuse the waste cold which is available from the regasification. This plant is expected to come online at some point in 2024. Having said that, our partner Highview Power already has demonstrated the technology through their pilot plants in the UK. And with that, I will end my short presentation, and I would invite all of you to connect with me and discuss further on LinkedIn or via email. Thank you.
Hello, so my name is Tomasz Gajatini, and I'm the co-founder and CTO of Re-energize. You can have the next slide, please. So the LDESS Council has done a great job, an amazing job of communicating to the wider public about the enormous size of the long duration energy storage market. So about how it's a multi-trillion-dollar opportunity. And this is very exciting, sure, but very important for us at Re-energize. It also speaks to the biggest problem that needs to be solved, which is how do we create a long duration energy storage solution that can scale to the enormous needs of the next 15 years and after. So to support the energy transition, we need at least 10 times more energy storage than has been deployed in the last 100+ years. And we need to do that in 1/10 of the time. So business as usual won't cut it. Re-energize starts with conventional pumped hydro storage, so PHS. We love this technology, and there's a very good reason it accounts for almost all of the global energy storage deployed to date. So we take PHS, which is established, low cost, it's reliable and low risk, and we make it scalable. By replacing water with a high density fluid in a closed loop system, we can build projects on hills instead of mountains. So next slide, please. Consider 2 projects, water and high density hydro. Both are at 100 megawatts in 6 hours in this case. And to enable a like for like comparison, both have been sized to yield the same levelized cost of storage, and IRR. But HD Hydro can achieve this with a 120-meter hill, whereas water needs 250 meters. And this is the key. So to support the energy transition, we need thousands of sites, and you will be hard-pressed to develop thousands of sites at 250 meters in the time needed. But you will find it much easier to develop thousands of hills at 120 meters of height. So we've done extensive GIS studies and conclude that there are more than enough potential HD hydro sites to meet the needs of the energy transition several times over. And that's why we say HD hydro is scalable. And this is where you can then unlock a virtuous circle. When you start deploying HD hydro in very large volumes, sites can be located where they make the most economic sense. You can now build smaller projects in parallel. Smaller projects are faster to build. Learning curves will reduce costs. And we're creating an LDESS technology that can be deployed in very large volumes very quickly and globally. Next slide, please. So thus far, we've developed our technology in the lab and in the field. We have 2 fully granted patents and a lot more in our pipeline. Our high density fluid has gone through extensive development program to ensure it performs to spec. That is to say that it's high density, it's low viscosity, and it's environmentally benign. And our multiple test rigs validate the HD Hydro system technology. And we've even run a small scale 5 kilowatt demonstrator on a ski hill. But all of this is just a precursor to the next big step, which has already begun. Last year, RheEnergise won the long duration energy storage competition funded by the UK government. And not only does this provide a very significant validation for our business, it's also enabled us to begin construction on a 500 kilowatt, 4-hour HD Hydro demonstration project. It's going to be near Plymouth in the UK on the site of a mine. Progress is going very rapidly. So our optimized HD turbine is soon to enter the manufacturing stage. Site works begin this summer in the construction season. The custom fluid management system will be tested later this year, and the overall project will be operational by the summer of 2024, so next summer. And by this point, our technology will be at a TRL level 7 or 8. So this has just been a lightning introduction to Re-energize and our HD Hydro solution, but we look forward to sharing more information with anyone interested. Thank you very much.
Great, thank you. My name is Michael Rooney. I'm Vice President at a company called Rye Development. Rye is the leading developer of new low-impact hydropower in the U.S. market. And for Rye, that's 2 business lines. One is mostly focused in the Mid-Atlantic and Southeast U.S., where we look at existing dam structures for small-scale retrofit for run-of-river hydropower projects. And the other, which I'll talk about here in a few minutes, with my few minutes, is our approach to closed-loop, I guess, traditional pump storage. So Rye is advancing a number of projects that are closed-loop pump storage projects. And a little bit about, we've mentioned pump storage on this discussion a few times. There's over 30 operating existing pump storage facilities in the US today. A lot of those facilities were built to backstop the nuclear fleet a few decades ago, and it's been about 30 years since a new pump storage project was built. The vast majority of the projects in the US are open loop, where they utilize an existing body of water, reservoir, lake, or stream from one of the reservoirs. What Rye is proposing is a number of projects that are completely closed loop systems. So non-consumptive one-time fill of the reservoirs, and then a small amount of water needed each year to offset evaporation. But the technology is pretty straightforward. It's essentially 2 reservoirs on the landscape separated by some amount of topographic relief. What we've seen in our work is that there are projects that scale with sort of a minimum of 400 to 500 feet of vertical relief. The round trip efficiency of these projects is in the 80% range, which is pretty significant. And certainly these projects can be designed to be extremely large, as our last presenter mentioned. But what we've really seen from a market standpoint, particularly on the West Coast, is projects in the 8 to 12 hour range from a duration standpoint is really sort of the sweet spot. So the technology is again proven and widely sort of understood by the utilities in particular. But essentially what you're doing is using off-peak hours to move water through a penstock or a large pipe from the lower reservoir to the upper reservoir. And then of course, when the grid needs the power, you're simply deploying that water from the upper reservoir to the lower reservoir, utilizing a series of reverse pump hydro turbines nested in a powerhouse sort of at the midpoint of the penstock. A few interesting things about the projects and sort of what we're pursuing. These are large infrastructure projects, and we expect that they'll have a useful life of at least 80 to 100 years. They all go through a national environmental review through a FERC permit. The Federal Energy Regulatory Commission reviews and issues the license and construction operations for all these projects. And again, this is just an extremely mature and proven technology. And what we've seen is a market for them on the West Coast. If you could go back one slide, just to highlight a couple of the projects we're working on. We have 4 projects currently in development. One located in Root County, Colorado, which we just filed a preliminary permit on. One located in southeastern Kentucky, which we're sort of at the midway point on licensing. And then 2 in the Pacific Northwest. The Swan Lake project I'll highlight. It's a 400 megawatt, 9.5 hour duration project in Southern Oregon, which we're expected to break ground Q1 of 2024. And the next slide. A few of the things to highlight just from an environmental standpoint, and we've seen this across our portfolio. You know, some of the benefits of pump storage is really relying on local supply chains, both on sort of building the projects, but also from a labor standpoint. Our project in Washington is sited on a former brownfield development site, and our project in Kentucky is at a partially active coal mine site. So really land reuse is a big part of the focus for the projects we're pursuing. And again, closed loop systems do not involve construction of new dams on lakes or rivers or reservoirs. And so this idea of a non-consumptive, completely off-water system really, is a huge benefit to the technology. And the last thing I'll say is, on the West Coast, we really see these projects moving from what they were in the past, which is, in a large part in the U.S. backing up nuclear fleet, really to a renewable enabling technology, particularly as states like California, Washington, and Oregon move towards 100% clean legislative mandates. So with that, I'll stop and happy to answer any questions. Thank you.
My name is Klaus Kruger. I'm a senior expert at Voith Hydro, the corporate technology center in Heidenheim. I'm working in a company who is working hydro business since more than 140 years. And we built the first pump storage power plant in 1907. Since that time, we have sold about 450 turbines for pumped hydro, and with a total capacity of 60 gigawatts. So next slide, please. For orientation, I will start with this slide from the International Energy Agency, which compares the installed storage capacity worldwide. These are the 3 most important technologies: batteries, pumped storage, and the classic storage power plants, which have a natural water inflow. On the left side, you can see the total installed battery storage capacity. This includes not only the stationary battery storages, but also all the batteries in electrical vehicles. So it is less than 1 terawatt hours. For comparison, the annual energy requirement in form of electricity in Germany is approximately 500 terawatt hour. So this means that all the batteries in the world could cover the electricity demand in Germany for only 1/2 day. In the middle, you see the total storage capacity of all pumped hydro in the world, showing the dark blue, which is 13 times larger than the battery capacity. If you compare these two numbers with a classic water storage power plants, a completely different picture emerges, because the total storage capacity is 1,500 terawatt hours, which is 2,200 times larger than all the chemical batteries. For me, the classical hydro storage facilities represent the largest installed LDESS in the world, fully integrated in the electricity sector. The main takeaways of this slide are the following. Existing and new reservoir hydropower plants and pumped hydro are the most affordable sources of flexibility today. Hydropower is the only low carbon power technology capable of providing up to seasonal bulk energy storage. And as a third, such capabilities will be essential for a cost-effective and secure operation of intermittent renewables dominated power systems of the future. Next slide, please. As mentioned by the other presenters before, classical pump storage, it's actually stores electricity in form of potential energy. So the basic principle of energy conversion is shown on this slide. In pump mode on the left side, which means charging, the electrical energy is taken from the electrical grid to feed a motor that mechanically drives a pump. The water is pumped from the lower basin into the upper basin. In the turbine mode, so during discharging, the water simply flows downhill via gravity and drives the turbine. The turbine then drives mechanically the generator rotor, and the electrical energy returns back to the electrical grid. Next slide, please. I will close my talk with this slide describing the reason why pumped hydro will remain a crucial element, mainly for daily cycling of bulk energy in electricity systems. Pumped hydro is the only proven large-scale power storage solutions operating since 1891. It is very durable and extremely cycle-proof. We are talking about a lifetime of 80 to 100 years, and with designs of more than 100,000 storage cycles. Important for the life consumption are the number of starts and stops. So we have a 6-digit number. In 2019, as mentioned by Julia, over 90% of the global storage power is provided by pumped hydro. Modern plants achieve, as also mentioned by other speakers, a high full cycle efficiency between 78 to 82%. Depending on the utilized electrical machines, pumped hydro can also provide synchronous or emulated rotating inertia, which is very important for grid resiliency. So even if a pumped hydro is not in turbine mode and is not in pump mode, it can rotate in the so-called synchronous condenser mode with a runner running in air and offering mechanical rotational inertia to the grid. Most of them can also provide black start capabilities for grid restoration purposes. And further, pumped hydro is also characterized by quite low storage costs. At present, 42 gigawatts of pumped hydro are worldwide under construction, mainly in China, Austria, Australia, India, Israel, and Morocco. Next slide. Thank you for your attention, and don't hesitate to ask questions.
Thank you all so very much. I think it was great to see the diversity again of the LDESS technologies. And if you all want to come back on screen, we can continue to answer the Q&A. There's been a lot of dialogue in the Q&A chat, so please check that out too. But I also want to highlight, what you heard themes about all the ancillary services that the technologies can provide, and the fact that there's a lot of commercialization already there, and really we have to focus on scale. So I'd like to hand it over to Suman. Are there any other questions you want to pull from the Q&A? And yes, the slides will be shared. I know there was one from Sumitomo that you wanted to answer live, Ashok. So why is the discharge capacity lower than the charge capacity?
Yeah, I just thought it would be too much to type out the answer, to be honest. So the reason the discharge, at least the example I showed, the discharge capacity was lower than the charging capacity is we basically looked at a situation where The plant would be co-located with, for example, a solar energy plant. So typically in many countries, solar is actually available for about 8 to 10 hours in the day. And then you have the remaining period of the day where you need to use the storage to provide, to basically shift the solar energy from the day to night. And so because the time period available for charging is quite low, we typically oversize the charging relative to the discharge capacity. So that's that was just an example we picked up, and that was why the capacity was 2 times the discharge capacity.
Thank you. And then for Tomas, how does your system LCOS, are they close to 10 cents per kilowatt hour or more?
So I guess I would start by saying, to a degree, the cost, the economics of a project is really a function, very site dependent. And what we were really saying in this slide is that we can make our cost and our economics equivalent to conventional pump storage. And we like to do that because everyone knows that conventional pump storage is really the gold standard in this case. And what we really wanted to show was that if you wanted to, you could make a project that have the economics of conventional pump storage, but you would need less vertical elevation. So to directly answer the question is, can you create a project that has a 10 cent cost per kilowatt hour? Yes, for the right site. But that's not the real message we're trying to communicate. We're trying to say we can do pumped hydro storage economics with lower vertical elevation, which means more siting opportunities.
And I think that's also a really good theme that from everyone, and just the size of the footprint and the ranges and the geographies, whether it's above ground or underground. Again, it's really important to kind of note, what's available, and also just the point that you heard from everybody about the emissions reductions and zero emissions. That's really important. So as more questions come in, I'd like to hear from all of you, like, what are you seeing as one of the biggest challenges or barriers to really kind of installing today, or in commercialization, or a policy that you'd like to highlight for all of us to continue to push on?
I can go. To be honest, I think that as soon as there are clear rules for offtake and long-term, let's say, a certainty of the revenues, the market will follow right away. And I think we have proven today that there are many technologies available that the moment the market can secure that offtake on the long run, everybody will be surprised of what this industry can do.
Yeah, I would just add that, for us, similar to what we've seen in California, where they've actually essentially done a carve out for long duration energy storage, allowing for there to be, competitive technologies across the board, but make it very clear that if you're going to increase the amount of renewables to achieve these carbon neutral goals or mandates that certain states are starting to put in place, I think that the only way you're going to get there is that you have some policy movement that establishes a role for long duration energy storage, and then let the best technology win.
If I can just quickly add something. So what at least we have seen in some of the markets we've been looking at closely is that everybody wants to go 100% renewable, and everybody wants storage, but very few people actually want to pay anything for it. They sort of think that the storage comes for free, or for like such a cheap price that it's usually not sometimes viable for some of the new technologies to sort of come in. So we were actually in India a few weeks ago looking at the market there, and what we observed is that many of the distribution companies are in poor financial health, and though all of them have issued some tenders for storage, it's usually a case where there needs to be some sort of subsidy or some sort of financial guarantee from the government to even make it viable for them. And this is not just considering long duration. This is even for traditional storage technologies which have been around for some time.
That's a great point.
Yeah, that's something we are seeing in some of the markets we are looking at.
the public-private partnership is really important, I think, for all countries. And that last slide that Klaus brought up of just showing, like, this is already being worked on. There's already projects that are, being constructed right now around the world, and pumped hydro innovative technologies that we've seen is really important. But keep pushing over the hurdle to scale is with the financing. Klaus, and then Tomas and Michael.
It is not only the financing and the revenues, also the permitting stage can take in some regions up to between 8 and 12 years. And this, you can imagine, we are not talking about construction. So permitting, it's a big issue. So we have to get down to maybe 2 or 3 years for the permitting phase. And in order to accelerate everything. But if we still continue with those long durations, this is really a big problem.
I'm glad you're.
So
Go ahead, Tomas.
And I think building beautifully on that. I mean, so we can say that, the need for long duration energy storage. I keep having the same message in all these sessions, but the need for long duration energy storage is not new, right? People knew this a long time ago, but it's just the way it goes. You need a lot more. The urgency of long duration energy storage increases with the rate of penetration of renewables, and we're getting into that zone now. And you see it in certain markets, perhaps Chile, for example, where the rate of penetration of renewables is really causing a huge need for energy storage. And what that means for the people on this panel is that suddenly this is going to become a burning crisis. And on my slide, I used the point of 100x, and it's true. If you take all of the energy storage to date, more than 10 times increase, and we have to do it in the next 14 years. And we're not starting today, so it's going to be even less. So increasing the rate of deployment by 100x is a huge, enormous challenge. And it doesn't get solved just by technology, and it doesn't get solved just by policy. It's got to be everything at multiple levels.
Well said. Michael, you wanted to jump in?
Yeah, I would just add, I think those are all great points. I would just add, I think, we've seen legislative sort of mandates on the West Coast around renewables, and then we've seen, states like California sort of taking a step further and actually having a carve out for long duration energy storage, which I think has been incredibly helpful for our work on the West Coast. I think the other thing that we've seen at least starting to shift, and we've been pushing on for a while, is depending on what market you're in, really helping and pushing on utilities to be able to think past the next 3 years or the next 5 years, right? And think about sort of the long lead times that are associated with not just pump storage, but sort of a number of emerging technologies, and really design procurement processes that are built for those types of projects and technologies to adequately sort of present their value, right? So, running an RFP that for a procurement exercise that has an online date of maybe 8 years out versus 4 years out, and sort of allowing a number of these technologies to compete in sort of a designed process that allows them to show sort of the comprehensive value of the asset. And so I think that we've spent quite a bit of time at Rye pushing on utility plans and RFP design and things of that nature, but I think we've started to see a shift, at least on the West Coast, for groups considering longer lead time resources. And so, that's been, I think, a pretty big positive for us. And then the last thing I would say is really kind of stressing the importance of a diversity of storage technologies, not just in long duration, but sort of across the board, right? And so if you imagine a future where, we have sort of all of our storage needs met on the West Coast in the next 8 years by, some form of battery storage or lithium-ion storage, what does that look like in 15 years or 20 years? And to other points made, I think sort of the diversity of, short and long-term assets, short and long duration assets is going to be critically important moving forward.
No, thank you, Michael. The diversity portfolio is critical, but I think the point of changing and updating the criteria and the request for proposals is something that is just must happen. And we're seeing it around the world, because of our changing times, or because of our new energy systems, whether it's behind the meter or in front of the meter, we have to change the criteria to adapt. And long duration energy storage, all the ancillary services and so much more that we can provide need to be accounted for and get credit in the markets. I know we have a few more minutes, but I'd like to kind of hear from everybody on, you know, this is, the scale is huge. It's a large road to climb, but we're making, you know, these efforts to really kind of put down the stepping stones to get there. And so, you know, having the knowledge base and the expertise of pumped hydro to really kind of affect mechanical storage. What's one lasting message you'd like to leave with the group of you know, what to take away of the value out of mechanical LDESS? Klaus, and then Chris, I want to go to you next because I haven't heard from you.
Yes, I think it is quite clear that long duration, it's a necessity for the energy transition, but we also need bulk energy storage. This is why I brought that example. So the total capacity of all the batteries in the world can only provide half day only for Germany. Imagine for the complete world. So the storage capacity must be increased, not only the duration, and also, so therefore the bulk scale, we need solutions which they provide 1 gigawatt of power for that long durations. That's the main message from my side.
Great point. My screen keeps moving around. So Chris, and then Francesco, and then Tomas.
I'm sorry, you're gonna have to repeat your question. I'm in a hotel and I have an unstable connection.
I'll come back to you, but go ahead, Francesco and Tomas, because we're talking about kind of what is the lasting message you want to leave for mechanical LDESS.
Yeah, I think the very important value added that this kind of technologies can add is actually the fact that we rely in most of cases on existing technologies that are being used and service the energy as a whole industry for more than 100 years now. And many of these people connected here, but and these businesses we have been used to put steel at work to produce energy, and we are keep on doing now to doing that for storing energy. And this is basically a plug and play solution really to solve a big problem that we all have.
Tomas,
yeah. So continuing that theme, you know, if we look at what the next 10 years might look like, it's a bit late in the day to invent completely new industries and supply chains and routes to market and routes to customers. So in our case, for example, it was a very strategic decision that we made the choice to build on the existing hydro industry, which is a global presence and already there. So yes, this idea that leveraging existing industrial capacity is critical to meeting the timescales.
Chris, do you want to go next, and then Ashok, and then Dean?
Yeah, mechanical solutions are efficient, they're safe, and they're available now.
Well said. Ashok.
Yeah, I think the others have already mentioned a lot of great points, but I think one thing which is clear about any mechanical storage technology, and I think this was repeated in all the presentations today, is the really long lifetime. Like, people are talking about 30, 40, 50 years. And most of these technologies don't require any sort of exotic materials, and they're not constrained by geopolitical risks or supply chains, which is becoming increasingly important as well. And they can contribute a number of additional services to grid stability. And I think the storage technologies can be used for all sorts of applications, whether it's off-grid, whether it's transmission level, whether it's looking at individual developers. I think the technologies are ready for deployment, and we just need the final push to really see it explode.
Thanks, Ashok. We're definitely pushing forward hard, that's for sure. Dean, and then Michael.
Yeah, I don't want to just reiterate what everybody else has said. What I think is beautiful about this is that what I've learned is that everybody here seems to be, you know, optimizing in many cases technologies that were already out there, right? Making them somehow better than what they were, kind of like the old BASF ad. We don't make it, we make it better, right? So I think that's beautiful. But what I think is also clear to me, including our own technology, is that, you know, the time to get projects across the finish line, the permitting process, the interconnection process, the siting process, the construction process, you know, we're talking in many cases 4 to 7 years for a project. And what I fear will happen is we're kind of like this pendulum, right? People will shift as quickly as possible, will ramp up as much solar, as much, on the back heels of where wind is already. And we're going to have this problem. And then suddenly there'll be policy changes that say, oh, you've got to go out there and solve this problem by implementing some long duration solution.
Right.
And I think it's an unfortunate event, but I think that's probably what will happen.
Thanks, Dean. Michael, last few seconds on the last word to close us out, but thank you all.
Yeah, I would just say, I mean, I think across the board here, right, there's a value to this type of long duration storage, and in particular, in the cases that we've seen, these are well understood assets from a utility and grid management standpoint, and I think that's actually critical to getting projects done at scale. And to Klaas's point, I think the need is so great that the ability to sort of bring a new version of existing well understood technologies into place to meet at least the immediate demand is critical.
Well, again, thank you all for joining us. Thank you to the panelists for sharing all your expertise and great excitement going forward. If you have questions, continue to reach out to the LDESS Council and look forward to our next webinars and conversations. But thank you all so much for pushing us forward. Hashtag LDESS. Have a great day. Bye.
Thank you.
Yeah, thank you very much. Bye-bye.
Ciao.
Bye-bye. Have a nice day.
You too. Thank you. Ciao.
Sumin Son, can you stay in the line for a short time?